Walk onto the floor of a modern industrial facility, and you aren't looking at a single operation controlled by one central computer. You are looking at a highly distributed environment, managed by specialized, local controllers. This network acts as a deterministic nervous system, executing logic loops in milliseconds to ensure absolute physical precision. Selecting the wrong architecture carries immediate stakes. Minor network latency causes physical collisions. Poor redundancy leads to catastrophic downtime, and inadequate segmentation exposes severe cybersecurity vulnerabilities. To navigate this environment, we rely on 4 foundational architectures: programmable logic controllers, programmable automation controllers, distributed control systems, and supervisory control and data acquisition. We evaluate each of these controller types across 4 criteria: their core operating principles, their structural architecture, their mechanisms for reliability, and the specific hardware deployed in the field. Understanding the boundaries of these 4 architectures is the only proven method for successfully scaling deterministic closed-loop process control. The Programmable Logic Controller, or PLC, is a ruggedized digital computer. It was engineered in the 1960s to replace complex hardwired relay systems, built specifically to survive extreme industrial environments. Its core principle is executing cyclic logic. The PLC reads a sensor input, executes ladder logic through its processor, and triggers an actuator output in milliseconds. Structurally, this requires a central processing unit, I/O modules, and industrial communication ports utilizing Profinet. A PLC achieves reliability through physical endurance. These units maintain exceptionally high mean time between failures by utilizing components specifically shielded against severe factory vibration and electromagnetic interference. This architecture excels in discrete, sequential manufacturing. When a facility needs to route materials along a conveyor or operate high-speed packaging equipment, the PLC handles the repetitive logic. You will see this hardware deployed globally in systems like the Siemens Somatic S7 series or the Schneider Electric Modicon lines. The PLC's primary function is localized, indestructible execution of discrete logic directly on the factory floor. As automation requirements scaled, manufacturers developed the Programmable Automation Controller, or PAC. This architecture bridges the gap between the rugged reliability of a traditional PLC and the advanced computing power of a PC. A PAC handles the same high-speed deterministic logic as a PLC, but it processes multi-domain tasks, incorporating complex motion control and vision systems within a single programming environment. This includes natively integrating PID loops. Modern PACs push position and velocity loop closures out of the central processor, directly down to the drive level. To achieve this, closed-loop servo systems use encoders to continuously return real-time rotational position data, instantly correcting any axis deviation. Siemens addresses this specific demand with drive-based controllers, scaling from the single-axis Simotion D410-2 up to the multi-axis D4552. In the United States market, the Rockwell Automation Control Logix chassis serves as the standard for discrete PAC manufacturing, frequently paired with integrated servo drives. These controllers are deployed in environments that require complex coordination, such as synchronized robotics and vision-guided assembly lines. PACs take standard sequential automation and elevate it into synchronized multi-domain orchestration. Moving away from discrete machines, we enter the continuous processing environments of oil refineries and chemical plants, which require a completely different architecture. This is the domain of the Distributed Control System, or DCS. It operates as a centralized supervisory framework distributed across an entire facility, deployed specifically where stopping production is not an option. The architecture is strictly hierarchical, building upward from field-level sensors into redundant control levels, ultimately feeding into engineering workstations. Within these nodes, the DCS uses PID controllers to manage analog variables, constantly regulating fluid pressure, temperature, and thermal flow. The defining reliability feature of a DCS is redundancy. To guarantee continuous operation, these systems are engineered with dual communication networks, dual power supplies, and dual processors. If one component fails, its backup assumes control without a single millisecond of interruption. Facilities implement this topology using heavy-duty platforms like the ABB System 800XA or Emerson's Delta V. The ultimate purpose of a DCS is guaranteeing zero downtime execution for volatile, continuous manufacturing operations. While a DCS manages localized continuous processes, supervisory control and data acquisition, or SCADA, provides wide-area geographic supervision. SCADA functions primarily as a software layer, aggregating and logging data from remote terminal units, or scattered PLCs, over vast distances. At this high supervisory level, SCADA often relies on open-loop control principles, providing human operators with the telemetry needed to make macro-level adjustments, rather than executing microsecond logic cycles. This architecture is transitioning towards software-defined systems, as industrial PCs and edge controllers begin to run in tandem with SCADA networks. These devices decouple the control logic from proprietary hardware. By utilizing soft PLCs, facilities can execute deterministic control on standard operating systems like Linux or Windows. Furthermore, industrial PCs act as edge nodes. They filter raw, high-volume factory data and push a refined telemetry stream directly to the cloud for predictive AI analysis and maintenance forecasting. You will find these edge nodes actively managing modern smart grids, municipal water treatment facilities, and extensive pipeline infrastructure. SCADA and IPCs decouple physical hardware constraints from system-wide data supervision. The historical borders between these architectures are collapsing. Modern PACs easily handle continuous PID loops, and DCS platforms effectively manage discrete I/O tasks. The modern industrial focus is no longer strictly on hardware specifications, but rather on the software ecosystem that binds these components together. Platforms like Siemens Xcelerator or Rockwell FactoryTalk unify logic, motion, human-machine interfaces, and digital twins into a single, cohesive environment. Despite this convergence, architectural selection rules remain. Deploy a PLC for localized, high-speed discrete tasks. Utilize a PAC for synchronized multi-axis orchestration, and a DCS for zero-downtime, continuous processing. Deploy SCADA for wide-area geographic supervision and data logging. Selecting an architecture is a long-term commitment to a digital lifecycle. The controller has evolved from a blind executor of logic into an intelligent, predictive node at the center of the modern.
In this session, module CAT-017 covers advanced circuit design. Don't forget to like and subscribe to stay updated with our latest tutorials.